In this video, we'll be discussing about the refraction of light. So let's read a little bit of theory here. The speed of light is different in different medium. So if you say the light speed in vacuum will be different, and if it is in water or glass, the speed will be different. So that's what it's been said here. The speed of light is different in different medium. So what happens when light enters from one medium to another? There will be a change in speed because the medium is different. So that is why this phenomena, changing of speed, we are calling a refraction. So remember, we have binded this concept of refraction with a change in speed. And the result of it, the effect of it, the visible result will be of this change in speed is bending of light when light enters another medium at an angle. Now let's understand that why that is happening. Now, for example, if you are here and let's say you have some speed and it's a flat ground and you are running here and then you see a different medium, let's say jungle. So it's a denser medium. So now what you are going to do, your speed will change or not? Yes, your speed will decrease. And also you will change the path because the medium is different, right? So you will not go straight, you will bend a little, right? You may go this path. And after this, what is happening? Again, the ground is coming, right? The jungle is over by now. Again, the rarer medium is now coming into the play. So you will again increase the speed because it's a flat ground again. You will pick up the same speed which you are having, and you may take this path now. So this bending of light or your change of path is due to what? It is due to your decrease in speed. Similarly, it happens with light. If you shine a laser light from here like this at some angle, and this jungle which you are thinking, if it is a glass, then the light will bend. The light will slow down, and that's why it will bend. And again here, the light is coming out of the glass. So again, it will bend, it will change its path. So that's why if you see the etymology of this word refraction, it means breaking. Uh, light is like kind of looking like it is not continuous, it is breaking at this point and then again breaking at this point. So that is what we are calling the refraction. But the reason is the change of speed. When light goes from one medium to a different medium, it will bend, it will reduce or increase its speed, and due to what, it will change its path. So that is how we can define the refraction. Now for the light coming like this and going to a different medium, now we want to know how much speed will be reduced. If glass comes, how much the speed will be reduced of the light. Now again, if it is in a different medium, it can be water also. What will be the speed of light there? If it is a diamond, another medium, light enters there, what will be its speed? So we want to know quantitatively what will be the speed of light in different mediums. So that is the first thing we want to know. And the second thing, which way light will bend. What will be the why light will take such path? It can go anywhere, right? So why this? Who's telling you to put line like this so that you know how much angle it will change, right? So which way light will bend and how much, that is also a question. We want a quantitative answer for that. And for answering that, these two questions, we have a concept of refractive index. What is refractive index? Let's discuss that now. If we have a medium and we know the refractive index of it, that number will tell us how much the light will slow down. So I have shown here a table where here is a medium, vacuum, air, water, glass, diamond, and here on the right side I have refractive index. So for vacuum we take it as 1. For air it is 1.003. For practical purpose we also take air as 1. Not much difference. And then for water, glass, diamond, the values are 1.33, 1.5, and 2.42 respectively. So if we know these values, like for example water, if somebody asks, okay, what is the speed of light in water? That is easily calculated if we know the refractive index of water. So it is 1.33, remember. So the light speed in vacuum is 3 into 10 to the power 8 meter per second. We just need to divide, if we want to understand what is a calculate what is a speed of light in water, just by this number 1.33. If you will ask what is the speed of light in glass, I will just divide the speed of light in vacuum, and I know it will be divided by 1.5 in this case. What about diamond? Speed of light in vacuum and then divided by the refractive index of that number. And here, if I solve these values, here I'm getting speed of light in diamond, here I'm getting speed of light in glass, and here I will get speed of light in water. So can you tell me where it is getting reduced most? Diamond. Because I see the refractive index is huge. So it will reduce this fraction 3 into 10 to the power 8 value by much as compared to these values. We can understand by intuition also, if any medium, the refractive index is very high. What does that mean? It means the speed is very low as compared to the speed in vacuum. So more the refractive index, slower the speed of light in that medium. So that way we need to understand this. So we have answered the first part of the question, like how much the speed of light will reduce. We can calculate that now. But let's come to the second question, how much the light will bend. For example, if a light comes from air and it goes into water. Second example comes from air to the glass. What is the difference? Where it will bend more. So that information is also given by the refractive index, but in the form of a law, which we call Snell's law. Snell's law. So we'll understand this law next. So let us understand what Snell's law tells. It tells that product of refractive index and sine of angle of light ray remains constant. The product will be the same across interface. Interface is a fancy word here, which is telling this border, this boundary, which is separating two mediums. So let's say this side is vacuum. Vacuum. This is our first medium. We can say medium number one. And here, the gray part which I'm showing is our glass, say. So glass. It can be water, any other medium. And this is our medium two. Medium two. So when light travels from medium 1 to medium 2, what will happen? So first let's incident a light ray. Let's say light ray is coming like this. Light goes straight. Think of a laser light, as you have seen green laser lights easily available on the shops. So that laser light, if it incident here like this, now it will enter the glass, a different medium, it will slow down, and due to that we will be able to see the bending. But now we need to answer how much. So the sense now is telling that refractive index and the sign of the angle of light ray will remain constant. So what will be the refractive index of vacuum? And 1, we can say medium 1, refractive index of medium 1 is 1. Okay, what about glass? Let's say we can take n2, refractive index of this medium will be 1.5. So we know the refractive index of these two mediums and we have noted it down. Okay, what about the sign of the angle? Which angle it is talking about? So the angle which this ray is making is not this angle actually. We'll not take this angle. In refraction, we will always take angles with the normal to the interface. So this boundary, we need to draw a I can draw a dotted line like this, and if you see, it is 90 degree, 90 degree normal V. That's why we are calling it a fancy word normal for 90 degree to the surface. So we'll draw a normal, and from there we will get this angle. So we can say this light ray is making angle of incidence or angle of incident ray is theta 1. Now, what will happen afterwards? Let's see. So what it is saying, Snell's law, the product of refractive index and sine of the angle. So if this medium we talk about, so that will be n1 and we'll multiply by sine of the angle. Now we know the angle we are talking about is with the normal. So this is the normal to the interface. So 9 theta 1, right? And now when it enters, okay, it enters a different medium. There also we can take the product of refractive index, then 2 and sine of angle, which a light will make with the normal. Let's say it is theta 2. So this product across the interface will be constant or it will remain same. So now the light ray will bend like this, like this. It will go closer to, it will not go straight, but it will go closer to the normal. So this will be our angle theta 2, right? And we take the product. So here n2 multiplied by sine theta 2 will be equal to n1 into sine theta 1. That is what Snell's law tells. And due to this law, this particular law, now we can calculate what will be the angle of refraction. So theta 2 is angle of refraction. This is angle of incidence. So this is angle of incidence, some fancy words here. And this is theta 2 is angle of refraction. So now you can ask this question like, if the light ray is going like this, it did not go straight. Why it is not going like that? Why you have bended it towards the normal? So the answer lies here. The product has to be constant. What does that mean? Let's say example. So if I say 2 into 4, what is the answer? 8. Now, if you need to keep the constant, the answer as product as constant, and if I change these values, let's see if I change one value, what happens to other? For example, if I increase this 2 to 4, what will happen to other value? It will decrease. It will become 2. Then only the product will be the constant. Let's me decrease this value. So if I decrease this value 1, I have to increase this value, right? I'll make it 8 so that my product remains constant. So that is why if you see the light is coming from vacuum to the glass. So what has increased? This value, right? Eta 1 has increased. Here it was 1, now it is becoming 1.5. So if this value we are increasing, the other value has to decrease. So sine theta will decrease, or we can say the theta will decrease because it wants to have a smaller angle. It will come closer to the normal. In this example, we saw the light is coming from vacuum to glass. What if the scenario is reversed? What will happen? Let's see. So let's say light is coming like this. If you want to say the angle, if you want to talk about the angle, I have to draw a normal to the interface. And let's say it is making angle this theta 1, right? And we know the N1, the glass refractive index is 1.5. And for vacuum, we take N2 because it's a second medium now. Light is entering into the vacuum, so it will be taken as 1. Now this product has to be constant. So let's see the angle will increase or decrease. So we say now I'm summarizing the Snell's law N1 sine theta 1. This angle will remain constant across the interface. This side product and this side product will remain constant. So N2 into sine theta 2. So now what I'm doing with the refractive index, let's see that. So am I increasing this value? So the N1 is 1.5, but N2 is 1. So I am decreasing this value, right? So what should happen with my angle, right? If you are decreasing one value, this value has decreased, its angle will increase. So that is how we are able to see where the light will go. right? It will not go straight. It is in the air. It will not go here because the angle will be lesser. No, the refractive index is already reduced. It has become 1.5 to 1. So our angle will increase. So the light will bend like this, and we can say it will go away from the normal. So this somewhat the diagram roughly it will be. But as of now, we have just talked about diagrams. Let's use some values and calculate exact angles for some numericals. So let's read our question. A light beam in air hits a sheet of ground glass at an angle of 30 degrees. At what angle is the light beam refracted? So we need to calculate angle of refraction. The angle of incidence or the light ray which is making it the normal when it's coming through air is 30 degree is given to us. So now let's draw a diagram. So I've shaded this part to show the denser medium of ground glass. So this is our medium. This is our medium 1, which is air, and N1 for the first medium, the refractive index is 1. So actually it is 1.0003, but approximately we take it as 1. Vacuum and air are the same thing for us. Okay, so now let's say a medium 2, which is a ground glass. The refractive index is 1.52. So if they are not given, you can take 1.5 also. But if they have given, use a specific value what they have asked for. So let's say they have given in the question the refractive index of ground glass is 1.52. Now we have to incident light at 30 degree. So be careful about it. First, you can draw a normal, and then try to make 30 degrees. 30 degree will be like this much. Let's say this is our 30 degree. This is our theta 1 actually. And this way the light is going. Now can you tell me the light will go away from the normal or go closer to the normal? It is a denser medium, rare to denser. You're going into the jungle, come closer to the normal. So the light will, instead of going straight, it will bend closer to the normal. So this will be our theta 2 which they are asking. Other way of seeing it, see the value of refracting index, it is increasing, so angle will decrease. It will go reverse. They are indirectly proportional. Okay, so let's use Snell's law for that. So that tells a cross interface, the product of refractive index to the sine of the angle which the ray is making has to be equal to other side. If you see, that is n2 into sine theta 2. This thing we don't know. We don't know the angle of refraction. That's what we need to calculate. So let's say n1 is 1. So I'm just, now it's math only, 1. The refractive index of air, and sine theta 30 degree is 0.5. But anyway, let's keep it sine 30 degree. And then it will be equal to n2, which is 1.52, multiplied by sine theta 2. Now what we can do, we need to calculate this part. So let's keep this part this side, and we can take this, and when it will go 1.2 that side, it will divide. So I can say sine theta 2 will be equal to sine 30. I'm just ignoring 1, multiplication of 1, and then divided by 1.52. Okay, now if I want to calculate this angle, theta 2, I have to take sine inverse both sides. So I can say if you calculate sine inverse of this value, sine 30 degree, divided by 1.52, you should get the angle theta 2 or the angle of refraction. So here we will use calculator. So let's bring my calculator here, and we will say, okay, sine 30, then we need to, okay, sine 30, and then we need to divide it by 1.52, 1.52, we will get some value. Remember, we have to take inverse of that, so that functionality is here. I will take sine inverse of this angle, and I'll get 19.2, 19.2 degrees. So see, angle has reduced. Let me close the calculator so you can see. So the value has decreased, angle has become less, because if you see, when light is coming from this medium to this medium, the refractive index is increasing, it means angle will become lesser, the light will go closer to the normal. That's what our hunch was, and this is what the diagram will look like. 19.2 degrees, somewhat like this. So this is our first question. Let's go to another question. So let's try this question. Let's read it. A block of unknown material, you don't know the material what it is submerged in water. Light in the water is incident on the block at an angle of incidence of 31 degree. The angle of refraction of the light in the block is 27 degree. So the angle is getting reduced. It means the refractive index will increase. Let's see, what is the index of refraction of the material of the block? So they have asked what is the index of refraction. We can use Snell's law to calculate that. So first of all, let's draw the diagram and put these data in that. Like for example, all everywhere water is there, and there is a block. Let's say this is a block which is submerged in water. So water is everywhere. So this is our medium 1. Light is coming from water, medium 1, and we know eta 1 is 1.33. Okay, and the light is incident at what angle? It's given 31 degree. So I will draw a normal. Let's say light is coming like that. So 31 degree will be like this. So this is 31 degree, theta 1. Okay, so now the angle of refraction is also given 27 degree. It is getting reduced like this, and this is 27 degree. And we need to calculate what is the medium 2. We don't know the name, what this block is made of, that is unknown. And N2 we can calculate this is also unknown to us. So let's see what we can do. So we'll use the Snell's law across the interface at this boundary. The product of refractive index and the sine of the angle will remain constant. It'll be equal. So n1 into sine theta 1 will be equal to n2 into sine theta 2. We know both the angles and we know one of the refractive index. So if we put those value, we will get the n2. That is what we want to calculate. So to calculate n2, I will keep it like that. So n1 sine theta 1 divided by, we will take that side, then it'll go in the division. So it will be sine theta 2 will be equal to n2. So we just need to calculate this part. So let me put some values here. N1 is 1.33. Sine theta 1 is sine 31 degree. And then we need to divide it by sine of theta 2. That is also is given 27 degree to calculate this. Let me use my calculator for this. So here is a calculator. So 1.33 multiplied by sine 31. Okay, so what is the value? Then we need to divide this value by sine 27. Sine 27. And let's see what we get answer as. So I'm getting 1.5 as my refractive index of the second medium, this one. So I'm getting this value as 1.5 approximately. So this value is around of glass. So my guess will be this material is made of glass because the refractive index is coming equal to that, maybe, or maybe some other material which has this much of refractive index.